Hello everyone, in this lecture we will study about CMFB using Triode devices. Okay, in this we will study about a simple feedback topology which utilizes the output common mode voltage to be directly converted to a resistance or a current which prohibit comparison with a reference voltage, and where V R on 7 and in parallel with R on 8 adjusts the bias current of M5 and M6. Okay, so the output common mode level sets this R on 7 in parallel with R on 8 such that ID5 and ID6 exactly balance this I9, ID9 and ID10. This particular drain current exactly balance the drain current in ID9 and ID10. Okay, the output common mode level sets R on 7 in parallel with R on 8 such that ID5 and ID6 exactly balance ID9 and ID10. Now we have this VB minus VGS5 of VGS minus VB minus VGS5 as equals to twice ID R on 7 in parallel with R on 8. Simply our Ohm's law, this V is equals to IR. Okay, now we can keep this value of RP as this 1 upon mu n cos W by L, V out 2 plus V out 1 minus 2 VTH, and VGS5 can be written as, that is the common mode CM level, by noting that VGS5 is equals to twice ID under root twice ID mu n cos W by L 5 plus VTH 5. Okay, now it suffers from several drawbacks, and those drawbacks are: the value of the output common mode level is a function of the device parameter. Okay, and next, the voltage drop across ORAN 7 in parallel with ORAN 8 limits the output voltage swing. And third is that to minimize this particular drop, M7 and M8 are usually quite wider devices, which introduce a substantial capacitance at the output. So this second issue, that is the voltage drop across R.7 in parallel with R on 8 limits the output voltage swing, can be elevated by applying the feedback to the tail current of the input differential pair. Okay, but the other two remains there. Okay, what we have done, if VB is higher than expected, then the tail current of M1 and M2 increases and the output common mode level falls. And since the feedback through M7 and M8 attempts to correct the error, the overall change in Vout CM depends upon the loop gain of the CM of the network. Now we can determine the sensitivity of this Vout CM to VB as described as D of Vout CM upon dVB, where M7 8 is in the triode region. Then this GM7 and GM8 can be written as mu n cox W by L 78 VDS 78, and feedback factor can be calculated as beta is equals to V2 upon V1 when I2 is equals to 0, which is equals to minus of GM7 plus GM8 R on 7 in parallel with R on 8. Now we can substitute all the values over here. We get this VDS78 upon VGS78 minus VTH, negative sign with. Okay, so this VGS78 minus VTH is simply the overdrive voltage of M7 and M8. Okay, now we get the sensitivity as VGS78 minus VTH upon VDS78, that because it is defined as 1 by beta. So this is an important result since VGS78 is typically obtained in the vicinity of VDD by 2, and this above equation suggests that VDS78 must be maximized, okay, to maximize this sensitivity, but as at the cost of the loop gain. Okay, so this is a simpler technique which shows how we can control the output common mode level. In the next lecture, we will study about modification of this to obtain more accurate definition of output common mode level. Thank you.